Yeah, you're next to me. Okay.
Solar physicist.
Yeah. He's trying to take her picture.
I'm short.
You can stand on the table.
Hello, everyone, and welcome to our first press conference. It is Science from the Shadow, NASA's initial findings from the 2024 solar eclipse. I'm Samson from the AGU Media Relations Office. We'll begin with the panelists giving brief presentations describing their work, and then we'll open it up to questions from reporters in the room, also online. And we will end at 9:45 or when there are no more questions. Slides and additional materials from the briefing will be posted to the Press Information Exchange on AGU Connect, and we'll drop a link to that in the chat. This event is being recorded, and the recording will be posted on AGU's YouTube channel and linked to the Press Information Exchange. Please bear with us should there be any technical issues. If you have any questions during the briefing, please email news@agu.org. All right, I'll now turn it over to our panelists. Thanks.
All right, so my name is Dr. Kelly Korreck, and I am the program manager for NASA's Eclipse efforts for 2023 and 2024.
Good morning. I'm Shadia Habal. I'm a professor at the Institute for Astronomy at the University of Hawaii, and I've been leading eclipse expeditions since '95, and my group is called the Solar Wind Sherpas.
I'm Dr. Sarah Kovac. I'm from Southwest Research Institute in Boulder, Colorado, and I'm the program manager for CATE 2024.
Good morning. My name is Dr. Nathaniel Frizzell. I'm an associate professor at the University of Scranton, and I founded and I lead the Ham Radio Science Citizen Investigation, or HAMSCI, and we engaged amateur radio operators across the continent and the world to use amateur radios to study the eclipse.
Hi, my name is Diego. I work at NASA Goddard, and I'm a subject matter expert on the nationwide eclipse ballooning project, or in short, an EBP. We try to detect eclipse-generated gravity waves in the stratosphere using radio sound.
Again, my name is Dr. Kelly Korreck, and I had the honor and privilege of being the program manager for NASA's Eclipse efforts over 2023 and 2024. And today I'm going to talk to you a little bit about the amazing science. We did a lot of engagement, and there were 32 million folks who lived in the path of totality, and many, many more traveled in order to see it. So we're going to talk a little bit about the science that we got from this eclipse. This image that you see here displayed, the first image in the package, the outer ring is the solar wind, or what we see during an eclipse. The inner is an image from an extreme ultraviolet telescope in space that can see the sun's active magnetic field. Now, why the science of an eclipse is so exciting and has been used for hundreds, if not thousands of years to really understand what's going on here is that white ring there, we don't have the instruments that can tell us very well if they focus on the inner, it's too bright. If they focus on the outer, it's too dim. So we actually use the eclipses as a natural way to see that missing part, to fill in the science of that active sun or sunspots that we can see with telescopes here on Earth, and then the hot outer corona and that solar wind that affects us throughout our heliosphere. Looking at where the path went, you might think that you only got science along that path of 15 states that had totality, but we were actually enabled by NASA's different platforms and the creativity and innovation of these and many other scientists to study both the Earth and the sun and the atmosphere during this time. For instance, the science activation groups impacted across the US. Every state had an involvement in this eclipse. The solar system ambassadors, as you see here, you can tell that where the path was because there is a concentration there because that's where the best science, the science of the sun and actually seeing that middle region can be done. But you also see science being done all over the US. There's also the globe observer image on the other side of the slide. And that again is concentrated. Those observers are concentrated on the path of totality, but you are able to contribute to the science no matter where you were in the United States. Again, with NASA being able to enable the science that we did with the eclipse, we launched a series of 3 rockets before, during, and after the eclipses, both eclipses, the annular in 23 and 24. So that was one way to allow us to study the sun from a higher platform. We also will hear a little bit about the plane experiments and using the NASA WB-57 in order to study that corona, as well as the atmosphere. And with that, I'll turn it over to Dr. Shadia Habal.
Good morning. My name is Shadia Habal. This first image was taken from the ground during the 2024 total solar eclipse. And what's remarkable in this image is just to show how much you can capture in an image during totality. At the top there's a very faint CME, which you cannot see in this picture because of the lighting, but there are myriads of different, what we call dynamic events that were captured instantaneously in this image. In addition to this white light image, we also use, there's a suite of highly ionized iron lines that enable us to actually map the temperature in the corona. So the one in the left is from iron 10, ionized 9 times, corresponding to an electron temperature of 1,000,000 degrees. The one in the middle is from iron 14 at 1.8 million degrees. And the one on the right is a combination of those two. Now you can see that if you were to just look at the iron 10, iron 14, you wouldn't have guessed that it's the same eclipse. So what's remarkable here is that they trace different structures depending on their temperature. Now, unfortunately, such unique observations are often jeopardized by poor weather conditions. And this was the case for 40% of our eclipse expeditions. Now, given the scientific importance of these observations, we have sought recently and to seek airborne platforms that would carry our imagers and spectrometers above the clouds. Our first successful technology demonstration was from a CATE in 2023, and it was funded by NASA, and the posters are in the session on Friday morning in SH51D. The second successful attempt, and so I should have said that the CATE actually had a spectrometer as a payload, and it was a very successful first technology demonstrator of the use of a CATE for eclipse observations. Now, the second successful attempt was to use the WB57. So this is, as Kelly was saying, it offered the opportunity for several payloads. In the front, the nose bowl in front of the cockpit, we had two spectrometers stacked on top of each other. And on the wings, there were these enclosures called spear pods, where we had the imagers corresponding to the iron 10 and the iron 14 spectral lines, which I showed you earlier. So what happened, unfortunately, the operations of the spectrometers in the nose bowl didn't encounter any issues regarding vibration or stabilization, but that was not the case on the spear pods because we didn't have the data before when we were preparing for this planning and the design of the payloads and the gimbals. So unfortunately, there was a vibration in the spear pods that were hanging on the wings. So out of about 600 images, we managed to salvage 20 50 millisecond exposures. And what you see on the left now is the iron 14. It's the example. Both iron 10 and 14 had the same issue and gave the same amount of data. Now, this is what we call on-band. What we have to do is we have to take one image at line center and another one about 30 angstroms away, and then subtract the two to remove the continuum. And the resulting image is shown here on the right. And if you think about it, this is an image which is equivalent to 1 second of exposure time, whereas the others I showed you earlier were 4.5 minutes. So also, as I said, the spectrometers operated extremely well. We had two wavelength ranges, the ultraviolet 350 to 500 nanometers and the visible 500 to 1100. Now, this is a very special design, spectrometer design. So you have overlapping orders, but here we show some of, we show on the left, we show some of the lines detected in the UV channel, and on the right, some of the lines identified. This is just a sample. So our goal for the future is to continue to capitalize on these two platforms, which we have already started and proven that the technology works. And so without any further ado, stop here. I forgot to introduce my team who are sitting here. So if you want to talk to them after thank you.
Good morning, everyone. I'm Sarah Kovac. I'm from Southwest Research Institute, and I was the project manager for CATE 2024, which was an experiment that set out to capture 60 minutes of totality as the shadow crossed the path of the US. So when, if you'll remember back at the beginning to Kelly's slide where we have that data gap in the middle corona, there's a lot of really interesting stuff that's going on there. Lots of dynamics. That's where the sun, it's where the solar wind is born. And there's a lot going on there, but it's a really hard region to study due to multiple factors in the way we observe the sun. But the moon gives us a perfect opportunity and creates nature's coronagraph, essentially, so that we can get all the way down to the surface of the sun so we can really see those dynamics. And the sun, you know, if at any given site when you're watching an eclipse, you only get a handful of minutes of data. And the sun evolves more on the scale of tens of minutes. And so this was the reasoning to do CATE 2024, which placed 35 community teams along the path of totality so that we could essentially create an eclipse relay race, whereas totality ended at one site, it started at the next. And so you would get 3 minutes plus 3 minutes, and that gives us our 60-minute movie of the corona. We did this by engaging with the local teams along the path. It's just not feasible to put 35 professional astronomers along the path of totality. And so following in the footsteps of CATE 2017, we recruited community leaders who helped us recruit more community leaders who helped us recruit our team leads. And those were the folks that were the boots on the ground doing all the work. And so those were the people that really made this project happen. They put in several hours of training, workshops. We provided them with all of the equipment that they needed, including the telescope, camera, laptop, all the other accessories that go with that. And we provided them with training workshops that they then took back to their local teams to host their own workshops, where they learned why the science was important, how to use the equipment, how to engage with the public, how to view the eclipse safely, everything from the ground up. We explicitly were looking for teams and people who were in underserved communities that may not have a chance to have access to science like this, and also where we could leave the equipment in that community knowing it would be used in the future. And so that's what led us to all of these teams here. So in the top left is actually our coordinator workshop. So those are kind of our the people who were overseeing the team leads. And then what I'm showing is just a variety. We had anybody from college students, we had middle school students paired with retirees, we had atmospheric scientists, we had people who were English majors. So we really had, kind of this wide breadth of volunteers that were on these teams, really committing a lot of their time to making this project happen. So we had an engineering run in 2023 during the eclipse in Australia. And so what this image is showing is the polarized light coming from the corona during that eclipse. So the color is mapped to the angle of polarization, and then the intensity or saturation of that color tells you how polarized it is. You'll notice that there are some spots on here, particularly in the prominence, where it's white. It's not oversaturated, it just means it's not highly polarized. And so eventually, this is what our CATE 2024 data will look like. But what I'm going to show you today is our preliminary movie, which is just in polarized brightness. And so you're going to see 3 sites that are all co-aligned, and you can see the moon as it moves across the sun. So different parts of the corona are exposed. So the first site here is in Texas, which is site 8. Okay, and then site 16 is in Missouri. And then the last one that we'll play is in Maine. And so this kind of shows a little bit of the evolution from Texas to Maine over that, 60-ish minute time frame. And so what I want to end with is that we had, so eventually we'll have these rainbow images for all of our sites. I'm going to flip through a few of them here so you can see them. But one of the things that I'm most proud of in this project is that we had 100% participation on Eclipse Day. We had over 225 participants from all walks of life, and everybody showed up, rain included. We didn't have any equipment failures. The only reason folks didn't get data was due to weather, and that's just completely outside of our control. And so what I would like to do is just end by really emphasizing that these volunteers, these community participants that we had were invaluable to us, and doing this kind of citizen science is really, really important. And it exposes, a lot of early career folks, younger folks to this kind of thing early on. And I also want to thank Dan Seaton, Derek Lamb, and Amir Caspi, particularly for the last 2 weeks, and doing a lot of the work that they did to get us these images. And I'm just very proud of what all of our volunteers were able to do.
Good morning. My name is Dr. Nathaniel Frizzell. I'm from the University of Scranton, and I'm here with my co-investigator, Dr. Gareth Perry from NJIT, and my collaborators, Dr. Mary Lou West, and from Montclair State, and Dr. Bob Spletta from University of Scranton. And this I lead the HAMSCI, Ham Radio Science Citizen Investigation, and this is a citizen science initiative that's not just about eclipses, but it's about joining together the amateur radio or ham radio community with professional space scientists. And the idea is that amateur radio operators are licensed by the federal government, by the Federal Communications Commission, as hobbyists to transmit radio signals that are very often affected by space weather because they travel through the ionosphere. And we're able to make use of the signals they generate and the data they generate to remotely sense the upper atmosphere, its connection to space, and the lower atmosphere. So for the eclipses, we created the HAMSCI Festivals of Eclipse Ionospheric Science, or the FOEIS. And this is not just one experiment, but a series of many experiments, some that the scientists or leadership came up with, and some that were more grassroots efforts by the volunteer participants. I'm going to talk about two of those experiments today, the Solar Eclipse QSO Party and our personal space weather station project. And here in this slide, you can see pictures of some of the hundreds of stations that amateurs set up across the nation to talk with each other before, during, and after the eclipse on the high frequency bands from about 1 to 30 megahertz. Now, how do eclipses affect the ionosphere? The upper atmosphere is photoionized by sunlight. So when you have ultraviolet energy from the sun hit the upper atmosphere, it will ionize the upper regions, say from about 90 kilometers up to about 800 kilometers altitude, and it will electrify that region. So if you take the ultraviolet energy away, that will create a drop-off in photoionization. You'll get an electron density kind of reduction in that region. And so this happens every day as you go from day into night. And then here you can see in the eclipse, from the April 8th eclipse, this is a model created by our collaborator, Dr. Joseph Huba, that shows the reduction in electron density as the eclipse passes over the United States. So how does that affect radio signals? Well, if you have a radio signal of the correct frequency, here we're showing 14 megahertz, those signals will not just go in a straight line, they will be refracted by the upper atmosphere. So in the lower left-hand corner, that represents a transmitter in Florida, and it's connected by a red line to a receiver in Wisconsin. And before and after the eclipse, you can see a red line where they're talking to each other. During the eclipse, the electron density reduction causes the rays to escape into space and communications to drop. So we use this idea to look at the observations of communications that happened over the entire United States as a function of frequency. So in total, for the Solar Eclipse QSO Party, we had over 52.7 million observations of communications over the United States for the entire day of the eclipse. And I've separated it out by frequency because lower frequencies, say from 1.8 to 7 megahertz, they saw improved communications during the eclipse, which you can see that little bump in the red box on the bottom, whereas upper frequencies actually saw worsening communications. One of the reasons it's really important to study the ionospheric phenomena is that is where all of our satellite communications and navigation pass through. So it's very important that we understand how that region behaves. It also helps us to understand the communication, the connection between space and the upper atmosphere. In addition to the project where we had radio stations actively communicating back and forth, we also have something called the Personal Space Weather Station Project, where we have receivers distributed throughout the continent, hosted by volunteers, and they're all listening to beacon stations such as WWV in Colorado, which is a standard station run by the National Institute of Standards and Technology. This particular standard station produces very precise frequency transmissions on multiple frequencies, and we can look at Doppler shifts or small changes in the received frequency, and we can remotely sense variability in the upper atmosphere. So all the way to the left, you can see these bright red signals and these oscillations. Those are likely traveling ionospheric disturbances moving through the night. And then off to the right, you can see an S-shaped curve, especially on the 10 megahertz and 15 megahertz lines. That's the effect of the eclipse on this data. And so we are now in the process of analyzing all this and comparing it to models and other data sets, such as the one you're going to hear about now.
Nathaniel, for providing the context. So yeah, so my name is Jie Gong. I work at NASA Goddard, and our project PI is Angela Destargins. She's at Kenya right now, so she couldn't come, and I'm gonna present the preliminary science results from this project. Okay, so our motivation to study the eclipse, because our atmosphere has a strong inertia. Every time it's perturbed, it always tries to go back to its a stable state. So you could imagine the most perturbation comes from the troposphere, like deep convections, for example, hurricane, and flow over mountains and winter jet. So these are the major gravity wave sources. They can generate gravity waves and propagate up into really deep into the upper atmosphere and couple the lower and upper atmosphere together. So that's why they're important because for the accurate weather forecast and climate projection. However, eclipse is different. Eclipse is a total column decrease, transient decrease of incoming solar radiation. It happens at every level, from the top of the atmosphere to the surface. So and eclipse happens really transient, right? So it's a challenge for us to detect eclipse generated gravity waves. And we also have questions like where it's generated gravity wave and how. So these are the major questions we're having when we want to carry out this campaign. So this project is a nationwide eclipse ballooning project, is supported by the NASA Science Activation Program. So this program supports mostly for education and STEM experience. More than 35% of the participants actually come from community college or minority institutions, and more than 50% of them barely have any ballooning experience. So this is a really good hands-on experience for them to learn about STEM. So in 2023, during the annual eclipse, we have a test run to set different pods along the eclipse path as a test run. The blue balloons are from the engineer team. They're testing their pterodactyls. And the orange ones are from the atmospheric science team. They launch regular weather balloons every hour instead of twice daily. And in 2024, we also have these teams. And just to point out that during 2023, we set four teams at the Albuquerque, New Mexico, and we asked them to launch balloons as a relay. So every 15 minutes, one team launched the balloon. So in that way, we can get a very high temporal resolution time record to study the gravity wave. And to mention another thing, over Albuquerque in 2023, it's clear weather. We got really nice data, which I'm going to show in a moment. And in 2024, many places along the eclipse path is impacted by weather. So it's hard to detect eclipse-generated gravity waves. This is a photo collage from different teams. You can see some teams experience not very well weather. They didn't see the eclipse. Some teams has really good weather. And yeah, all of them have to launch balloons for a continuous 30-hour period every hour. So all of the teams stay overnight for both the campaigns. And that's really a large commitment. This is a photo from the engineer team. They carry a 360-degree camera. So the camera captures the eclipse at the far background. So this is a preliminary result showing from the 23 events. The horizontal axis is the time. The vertical axis is from the tropopause to the stratosphere. So the top panel is from temperature. The bottom panel is meridional wind. So you could clearly see the wave patterns without, playing any filtering of the data. We already can see the waves in the stratosphere. And we can also see the strong eclipse forcing during when the eclipse happens, the strong perturbation forcing in the wind field. And we speculate that this little jump could possibly be the eclipse-associated gravity waves, and the source is possibly in the tropopause. So this is a figure showing you the time series of tropopause change. The two red lines are sunset and sunrise, and the black line is eclipse. So you could see when the sun sets down in Albuquerque, the radiative cooling actually caused the tropopause to drop down immediately. And after sunrise, the tropopause goes back. And during eclipse, you can see another little drop down and goes back, right? So it fits our common understanding that eclipse is basically a small mimic transient sunset and sunrise. So the tropopause response shows you this. And on the right is the upward fraction of upward propagating gravity waves. The blue line is from the troposphere segment. So remember I said that most of the gravity wave sources are in the troposphere. That's why the blue line is constantly about 50%, except during the eclipse. During the eclipse, you can see the blue line drops down quickly, right? But the stratosphere upward propagation, it remains the same or even increases. So that means that there's a source in the tropopause that's radiating waves at both sides. So you can see from the schematics that in the troposphere, the response is actually everything quiets down. The weather or other gravity sources quiets down for a moment. But in the stratosphere, you can see the eclipse-generated gravity waves. And lastly, I want to show the student survey before, which is the blue bars, and after, which is the orange bars. So the left figure shows you how confident the students in getting about themselves in getting a job after graduation. So you can see before the eclipse, about 20% of them think, oh, I cannot get a job. And after the eclipse, more than 80% of them think, okay, I can get a job after graduation. The right panel showing you how they believe their interest, their expertise overlapping with STEM. So before the eclipse, about 45% of the students think, oh, I'm not a STEM person. And after eclipse, you can see, again, about 80% of students think I'm a strong STEM person. So that's, the positive impact to the students. So yeah, that's about it. Thank you.
Thank you, panelists, for sharing your work with us. We'll now open it up to questions from registered reporters. When asking a question, please state your full name and affiliation. For reporters online, please use the Q&A box, not the chat box, and we will invite you to unmute to ask questions in the order it was received. If you would also just like to type your question into the Q&A box, we can ask that question for you. We'll continue to take questions until 9:45 or until there are no more questions. So let's start with any questions in the room. Any questions online right now, Becca? Invite any other questions from, open it up to anyone in the room.
So thank you very much. My name is Christina Reed, and I'm a communications officer with the National Institute of Standards and Technology. And my question is for Sarah. And I wanted to know, with the images that you received, sorry if I missed it, but what do you do with that? Like, what's the next step?
Yeah, that's a good question. So what we're looking for lots of different things in our data, but one of the main things is looking just for evolution in that inner and middle corona region. So that is a transition region where the sun goes from having closed magnetic field lines where all the material comes back to the sun into open magnetic field lines where that is born into the nascent solar wind. And so we will be looking at basically how the corona evolves in those 60 minutes in the middle corona.
If no one else is asking a question, I'm going to. This is Karen Fox with NASA. I'm curious, Kelly, that was a really striking picture at the beginning of showing where you can't see the corona close to the sun. I'm curious if you have information about what's coming up in terms of coronagraphs or other possible ways of getting at that very low area.
Question, Karen. In terms of getting at that area, first of all, we do have some chronographs, and our friends at NOAA also have chronographs that are going up there. But importantly, we have Parker Solar Probe on December 24th, 2024, later this year, going into some of that region to actually directly sample it. And so that we were able to start making those connections of the sun and its surface activity, and then that middle corona region.
I think we have one question online.
Yeah, we have a question online from Rick Lovett, who we've asked to unmute himself.
Yes, okay. Can you hear me?
Yes.
I'm sorry, I can't hear you.
Yes, we can hear you.
Okay, sorry about that. So thank you very much for this. I have two questions if I can. I think they're kind of related. I'm curious how much we can learn from this, or what exactly we're going to learn from this that we can apply to, I don't know, weather forecasting, our knowledge of space weather. It looks like it's fairly preliminary at the present moment. And the second one is how, more specifically, will this interact with Parker's approach to the sun?
Who would like to take? Yeah, you take it first.
Okay, as far as what we're learning from regarding space weather, what we found that every eclipse image, and as Kelly was describing, we're probing a region of the corona that no other instrument, unfortunately, at the present or in the near future is going to probe. And this is, it's like capturing the initiation of a CME at different stages. So every eclipse image gives us a different view, captures an eclipse at different distances from the sun, some starting very, very close and some further away. So that kind of pattern of evolution is unique to the eclipse observations, and it gives us new insights into the evolution of CMEs. More importantly, which we didn't have time to discuss here, is really the role of prominences. So prominences are the coolest material in the corona, and they're enshrouded by the hottest material there. And they are very dynamic phenomena. And I mean, you have to go through models to try to understand, but still we don't have the full understanding of how the magnetic field really is so dynamic where prominences are located. And when they erupt, they push this shroud ahead of them and they form the coronal mass ejection. But the core is really formed by the prominence that stays connected to the sun. So it's only during a total solar eclipse that this full sequence of an eruption and a prominence forming the core of a CME and still attached to the sun that was ever reported.
Anyone else want to jump in?
Yes, so I'd like to say another thing about things that we can learn from this. And one of the things we are trying to do is really understand our Earth system and its atmosphere and its relationship to the sun. And of course, we know a tremendous amount about this, but there's also so much we don't know. The Earth's atmosphere and its connection to space is a tremendously undersampled system. One way that you can understand systems is by putting different inputs into it and seeing how the system responds. An eclipse, every single eclipse is a very unique input to the system that we only have one or two chances, to get that particular input. We get the day-night input every day. We can look at that, but these eclipses are very unique. So scientists from all different levels of the atmosphere are taking this opportunity to see how this known unique input affects the upper atmosphere and the atmosphere, and then we're using models to test how well do we understand what the physics are behind this response.
Great. And how this relates to Parker, I think of it as the old adage where different people sensing different parts of an elephant, right? You're blindfolded and you're feeling an elephant and it feels one way or looks one way. And when we look at the eclipse remotely and we see that middle corona, we're like, oh, that's the shape of this. Now, but is that flat on the sky? How is that? So I'm sensing that corona from one thing. Where Parker goes into it, we then have another viewpoint and we say, oh no, we've sensed this part over here. And maybe that wiggle or that bump that you see see in the eclipse image isn't exactly what you think it is. So that's why we need that system. And in understanding how our star works and how that wind is blown off, it's also related to astrophysics. It's about the stars in other places. It's also affecting our atmosphere, and these changes, and like Nathaniel was saying, is those little deltas or changes in inputs. We can then also start thinking about planetary atmospheres and other habitable worlds. So we can use these types of inputs for that type of science. And then Earth science in and of itself, right? And space weather. So you've changed the UV input into the sun, into the Earth, or you've kind of shook the ionosphere. What do we do to better our communication so that when space weather does that, we can do this? So the eclipses serve as a really great way to get that information and to do those little experiments along the way to get more understanding.
Oh, I think she was first. I'll come back to you.
Thanks. Hey, I'm Liz Landau. Thank you so much for this awesome presentation. I was just wondering, are you going to be comparing your data to the 2017 eclipse? Was any of this done back then? Did you expect anything different? And then are you going to be repeating any of these experiments for the next eclipse when it's in Europe? Thanks.
Yeah, so the CATE project that I talked about actually was pioneered way back in like 2014 in preparation for the 2017 eclipse by Dr. Matthew Penn, who at the time was at the National Solar Observatory. And in 2017, it was more solar minimum conditions. And that experiment also only took images in white light. And so the polarized images that I showed give you direction of light, which helps render more of a 3D picture of the corona, whereas white light gives you more of a 2D image. And so we will be comparing, we have observations from the 2017 eclipse in white light, we have the 2019 eclipse in polarized light, and then for future eclipses, Australia is going to be a really great place for the next few years. They have several eclipses, and so we're hoping to maybe partner with some people over there to see if they would be interested in doing something that my PI loves to call citizen mate. We also are looking at opportunities to engage our citizen science teams with maybe some schools in Spain for the 2026 eclipse. Really trying to, we have this niche community now with all of these teams who have all this experience. And so being able to share that with other parts of the world would really be excellent.
At HamSci, we did run the Solar Eclipse QSO party for the first time back in 2017, and we published those results in Geophysical Research Letters. And so we've already started comparing the data from that eclipse to this one. And we have a postdoc, Gareth and I, Dr. Kuldeep Pandey, who's working on that now. And we can already see differences between the data that we collected in 2017 and the data we collected now, much of which is related, we think, due to our phase in the solar cycle. That's certainly one aspect, and also possibly the path in which the differences in the path in which the eclipse took. So yes, we're definitely looking at that. Another difference between 2017 and now is we've significantly expanded our experimental efforts for these most recent eclipses. Back in 2017, we only did the Solar Eclipse QSO party. Now we have this whole Festival of Eclipse Ionospheric Sciences with this robust personal space weather station network, which has just been built over the past few years. We don't have strong plans for doing efforts in other countries right now for other eclipses, but we are looking for amateur radio volunteers in other countries that might be interested in doing this work over there. So we do have some efforts. One of our collaborators did just send a graduate student down to the Falkland Islands for the eclipse that just happened about a month or so ago. And so he had a poster yesterday with some very nice early results and some great photos from that trip.
Yeah, so for a nationwide eclipse ballooning project, we actually started to have a few teams started from 2017 and 2019. We had a paper published for the 2019 gravity wave. And in 2020, we flew to Chile and overcame all the COVID lockdown. And however, we were impacted super heavily by the atmospheric river event. And that's where we got the lesson learned that we cannot just have one or two pods. We have to have a lot of them in order to, tease out all those weather impacts. That's why the lesson learned has a big role playing in designing the 23 and 24 Eclipse campaign sites. And for the next spring Eclipse, we are already planning to write some proposal. Our team, wants to. Thank you.
Great. I think we have time for one more question, and we have an online one.
Is this on? Yes. From Morgan, from Business Insider, for Gia, can you talk more about the implications of your findings, particularly for weather forecasting?
Oh, yeah, that's a great question. Yeah, so I think the analogy I'd like to use is comparable. This scenario is comparable to detecting the gravitational wave. Gravitational wave, you got to detect a very faint signal out of a very loud cosmetic background, right? And for us, we need to detect a very transient and faint signal out of a very loud atmosphere background. So the confirmation of eclipse generated gravity waves using the 2023 data is actually confirmed that we can actually detecting it using a wise strategy. And another important thing is this is the for the first time that we are able to see a strong tropopause response. In the 2024, although the data is impacted by weather, we do see planetary waves propagating along the tropopause that we didn't expect to see. So there are a lot of interesting signs going on with the tropopause that the traditional radiosonde, twice daily radiosonde couldn't tell you. And these are all very important for the weather forecast, especially for the understanding the connection between the troposphere and the stratosphere. Yeah.
Then Morgan has a quick follow-up.
Sure.
Hi, thanks for talking through that. So am I correctly understanding that you're saying that the changes that eclipses make in the tropopause, are you saying that solar eclipses can affect weather on Earth? It's not just space weather, it's also our weather that we experience every day, or is that too much of a jump from your research?
It's not too much jump. It's actually we have ground stations from several of the pods, and we do see a strong perturbation, not just the reduction of incoming solar radiation, but a strong gravity wave pattern in the surface, near the surface. And one interesting thing, I was sitting in upstate New York. I didn't see the eclipse because of the cloud blocking, but I do feel that once the sun starts to settle down, all the mosquitoes came out immediately. So that's the biosphere and the planetary boundary layer interaction that you could actually feel during the eclipse. And I'm not sure if you're aware, but NASA Earth Science is investing in the decadal survey incubation program in the planetary boundary layer mission for the next decade. And these are some of the things that the PBL science can actually study. And so yeah, that's brings a lot of implication for weather. For weather forecast and observation.
Yeah, there was also the GLOBE Citizen Science Project out of NASA and NSF partnership, and they recorded cloud changes as well as temperature changes during the eclipse.
Great, I think we've hit time. Thanks everyone for joining us today. This concludes our press conference. Next event is media availability, all about chasing atmospheric rivers at 10 in the Media Roundtable room. And please join us at 11 for the 2024 Arctic report card from NOAA. Thank you.